Hey everybody, Mr. Piercy here. What we're going to start talking about in this lesson is we're getting into our first concept in our new unit where we're getting into reasoning, how we think about things in geometry. So the hierarchy starts with, a postulate, a statement I can accept to be true, a theorem, a statement that is true, but I have to kind of explain why it's true. And then we get into conjectures. Well, a conjecture comes from the idea that we can see a pattern emerging. The way that we see a pattern emerging is known as the idea of inductive reasoning. When you're practicing inductive reasoning, you're really looking to see, well, how do things happen? Is there something I can use to exploit here as far as a pattern that I can see and therefore make predictions with? That's really what inductive reasoning is going to be doing. And again, a conjecture is really just, okay, so I see this pattern emerging. Now I make a statement about it. That's really what conjectures are. So here is just a very simple, basic example of what inductive reasoning is. Well, you eat pizza for dinner every Friday night, so you're eating pizza for dinner, so it must be Friday night. Okay, it's just a pattern that you're using to take advantage of and therefore make a prediction with. Now, here is an example that we have. Before you actually start working all this stuff out, you probably might want to just have a scratch sheet of paper somewhere handy, because that's what we're talking about here. We're looking at a pattern, and we're going to make a conjecture out of it, and it's based on how many rectangles can be formed when you fold a piece of paper in half. So what I'm going to want you guys to do is in your notes, make sure that you have a piece of paper handy if you need to, and go ahead and start filling out the table. Identify the question, identify the answers that you think are going to be what you need for the questions that are here. So fill in the table, look at the pattern, okay? Based on the pattern, tying into our algebra skills, is it a linear pattern, a quadratic pattern, or an exponential pattern? Okay, well, depending on what type of pattern it is, from algebra we should be able to write an expression for it. Okay, and then we can use that expression to make predictions. Identify what's a reasonable domain and range. Now there's that term reasonable. Okay, it's different than what the true domain and range of a function would be. And then finally write a conjecture. So I want you guys to pause the video, take as much time as you need, and I want you to try answering these questions before I start revealing what my values are, what my numbers are, or what my answers are. Okay. And if you happen to be in a class where you can communicate with somebody, then go for it. Work together. Otherwise, go ahead and pause the video and let's see what you come up with. And when you're ready, come back. Okay. So I'm going to just trust everybody's doing what I'm asking you to do, and you have done your best to fill in the first page here, and you have some answers that we can share. So following the pattern, if you're folding a piece of paper, when I folded it twice, I had 4 rectangles, and then 8, and 16, and then 32, and for 6 folds, we would have had 64 rectangles. So the pattern, is it linear, quadratic, or exponential? So here, this is going to be an exponential expression. It's an exponential function. How do I know that? Well, partly what I'm looking at as a math person is I'm thinking, okay, well, what are the differences? What are the consecutive differences between my numbers? Because that way I can kind of determine, well, if it has a constant rate of change, we would say that that's a linear expression. If the second differences are constant, we would say that's quadratic. And the only other function that you've really studied from Algebra 1 so far would be exponential. So at least by process of elimination, you might be able to get to that one. So for the independent variables, the differences are always 1. 6 minus 5 is 1, 5 minus 4 is 1, and so on. Now if I say 64 minus 32, that gives me 32. 32 minus 16 is 16. So we can see pretty quickly that the rate of change is not constant. So we can rule out the fact that it's linear. So these are what I have right now are the first differences, and that's what we would use to see whether it was linear or not. Now what I'm going to do is I'm going to look at the second differences of my dependent variables and see if those are constant. And 32 minus 16, well, that's 16. Here I have an 8. Here I have a 4. Here I have a 2. And here I have a 1. So the second differences aren't constant either. So it means it cannot be a quadratic function either. So that is one way that we could use to determine what type of pattern that we see, whether it's linear, quadratic, or exponential. We're just using properties of those functions to say, well, if the first difference is constant, it's a linear function. If the second difference is constant, then it's quadratic. And well, the only other option that we have here in this case would be exponential, so at least we can say process of elimination gives us that. Well, now that we've established what type of function it is, what's the rule for it? What's the algebraic expression for it? So this is what I put. I said R of f is equal to 2 to the f power, where I'm writing this kind of in function notation. Okay? So function notation, if you remember, you might have said y is equal to x. Well, I could also say f of x is equal to x. This is what we refer to as function notation. So if you had said just like y is equal to 2 to the x power, that would have been fine. I'm just writing it based on the values that we have for our initials. Here I have folds, here I have R, or F for folds, R for rectangles. That's where I'm coming up with those R and F in my function. Okay, so how many would there be after 8? Well, after 8, there would be a total of 256. And I typed that wrong. The answer is 256, and this should be an 8 here, and that should be an 8 there, because it says 8. 256 is right, because I did do the math. I just wasn't paying attention, I guess, when I typed it up. So what is a reasonable domain and range? Well, reasonable, you know, algebraically speaking, we can have a whole lot of numbers for our domain. An exponential function has a domain of all real numbers, but realistically speaking, I'm probably going to say between 0 and 10 because, well, I can't have a negative number of folds, and probably once I get to 10 folds in a piece of paper, I really can't do any more. So that would give me a range of about 1 to 1024. And a conjecture that we could write here about the pattern, well, here the number of rectangles formed by folding a piece of paper in half can be found by taking 2 raised to the number of folds made, meaning the algebraic expression that we had back in the earlier problem. Okay, so we're going to take a pause here, and I'll come back in the next lesson where we'll take a little bit more time talking about inductive reasoning and how it works. But until then, guys, if this has given you any pause to say, oh, hey, there's a lot of algebra here that I really might need to brush up on, go ahead and do so. But we'll go ahead and take a pause for this lesson, and we'll come back here shortly with the second video. And again, if you have any questions about anything you've seen so far, make sure you write them in the comments or send me an email, and I'll be happy to talk with you about it. But until next time, guys, thanks for watching and take care.